we go. Here's our topic. Here's our objective. And if you know something's a molecule, if you know it's electron geometry, then our goal is to see how these electron geometries, there's only 5 of these, but then all the shapes fall into one of those 5. And that's what we're going to do. All right. I just said. All right. So the 5 that there are these names, and you might recognize them. There are actually molecular shape names as well. But these are the 5 electron geometries, and what makes them different is the number of domains in the molecules, or the number of domains off the center atom. All right. So for linear, the classic linear molecule is hydrogen dioxide, hydrogen gas. This has 1 domain, so that's a linear molecule. All right, and it would look like that. That's what its electron, how I draw the domains. Another example is ethine, where it's 2 domains, and that would look like that, and that's also called linear. Trigonal planar, the classic trigonal planar molecule, it's got a trigonal planar structure and shape, molecular shape, is boron molecules. This is boron trifluoride. All right. Now, to see how the other ones are beneath, or kind of housed within this trigonal planar electron geometry, you're going to add one of these bonding pairs up here, or bonding electrons, becomes an unbonded pair of electrons, and that is like a sulfur dioxide. These electron geometries, these sticks, could be a single or a double bond, as you can see. The overall shape of where the electrons are doesn't change, but the molecule's shape changes, in that becomes a bent molecule. All right. I'm drawing like the electron geometry with the lone pair, and then without it. Then if I add another lone pair onto my trigonal planar electron geometry, I get a linear shape. All right, that was oxygen gas. Now, tetrahedral, its electron geometry looks like this, just like a tetrahedral molecule. And if I add a lone pair, becomes trigonal planar. All right, you add that lone pair, comes up, and this is ammonia, NH3. All right, that's trigonal pyramidal shape, as it says there. And then if I add another, you can see this is water. That's the classic bent shape of water. All right, and there's with the lone pairs, there's without it. All right, if I add a third lone pair to this tetrahedral electron geometry, this is hydrogen fluoride, hydrogen chloride, bromide, iodide. These are all the halogens bonded with hydrogen. It looks like this. All right. Trigonal pyramidal is when I've got 5 electron domains. Phosphorus pentafluoride, it's going to look like this. That's what its electron geometries are going to look like. If I add a lone pair, I get the seesaw shape. It's going to look like this. This is sulfur tetrafluoride, and that's what it would look like, how you would draw it. All right, and there's it without the lone pair, and there's its shape. All right, now if I add another one, you can see that becomes my T shape. This is chloride trifluoride. There we go. If I add another one, now it assumes its linear shape. All right, that was the same linear shape of ethene or ethine. Now our last electron geometry is octahedral. This has got 6 domains. This is a compound sulfur hexafluoride. All right, and now when I add a lone pair, this becomes the square planar shape. No, not square planar, square pyramidal. All right, that's how you would show the electron geometries, with or without the lone pair, and there's the name. If I add one more, this becomes the square planar shape. This is xenon tetrafluoride. All right. Okay, here are my sources, and thanks so much. And let me know if you have any comments or questions.